of these in class, but I wanted to give extra examples about forces, even if we don't get through them all in class, so that you have access to them on Schoology. So these are going to be the notes that I take my examples from. So I've got examples 0 through 5. So sample or example 0 is a student sits in a smooth rolling chair with a combined mass of the student and chair of 80 kilograms. The student then grabs a 10 kilogram fire extinguisher and, just for fun, turns it on and propels herself with an acceleration of 0.25 meters per second. What's the force applied by the exhaust of the fire extinguisher? So the general formula for Newton's second law is acceleration is equal to net force, and it would either be total mass or mass of the system. So we're going to think of the system as being the student and the fire extinguisher, since they're one object. So I'm going to rearrange that. So the total mass of the system is 90 kilograms. The acceleration is 0.25 meters per second squared. So the net force of the fire extinguisher is 22.5 newtons. In real life, would you expect the acceleration to be somewhat more or somewhat less if this was really a thrust of 22.5 newtons, and why? I would expect it to be less, because even if it's a low friction chair or a smooth rolling chair, which implies minimal friction, there's still probably some friction, and that friction would oppose the motion of the object. And in real life, do you think the actual thrust for this problem would be provided would be a bit less or a bit more? That depends whether on the fire extinguisher. So I kind of don't like that question as much. I think what I meant to say here is, would the acceleration be a bit less or a bit more than what was listed? But with this one, I guess I'd say to get this acceleration, if there is friction, that means the thrust would have to be a bit more. So sample 1, Batman of mass 80 kilograms accelerates upwards at 3 meters per second squared due to the thrust on his jetpack. So we're going to assume Batman and the jetpack are 80 kilograms. Ignoring air resistance, A, draw a free body diagram, B, determine the amount of thrust. So for A, the thrust has to be greater than the gravitational force, which is mass times acceleration due to gravity. So I can put FMG, I can put F Earth, I can put F gravity, any of those are fine. And the thrust is pointing upward. So I'm going to start with Newton's second law to find the amount of thrust. So it's F net is equal to the mass of the system times acceleration. Well, the thrust is pointing upward and the gravitational force is pointing downward. And that equals the mass times acceleration. So I'm going to split up those forces. The thrust is acting upward, mg is acting downward, m times acceleration is the net, equal to the net force on the system because of the acceleration that was given. So this is the acceleration. That's a result of the net force, which is on the left side here. So I know 80, that's times 3. I know there's a force downward caused by gravity of 80 times 9.8. Again, you could use 10 if you want. So thrust minus 784 newtons of gravity down would equal 240 newtons of net force. So the thrust has to be 1,024 newtons. Does it make sense? Yeah, the upward thrust should be significantly greater than the force of gravity down for the object to be accelerated up. And it's not ridiculously greater because the acceleration up is only 3 meters per second squared. So this should be 30% more approximately than this. Sample 2, we've got vine 1 and vine 2. They're each at 60-degree angles from the horizontal. We've got Tarzan hanging here. Tarzan's got a mass of 100 kilograms holding onto those two vines. Find the tension in each vine. So this is going to be both a vector problem and a force problem. Overall, if he's hanging out there, it's static, which means the forces are balanced. So first I'm going to find Tarzan's weight, which is the force downwards, m times g. So that's 980 newtons down. Again, if you choose to use this as 10 newtons per kilogram, that'd be 1,000 newtons down. You do want to recognize that the vertical or y components of the tension in each of the vines must pull upward against Tarzan's weight, and the total vertical components up would equal his weight down. Now I'm going to write an algebraic equation for this. So I'm going to say T1, so that's tension in vine 1 and tension in vine 2. the vertical components equals the weight. So if I think about this, this is a 60-degree angle, and that's the tension is along that line. Then I can think of drawing a triangle and a right triangle where this vertical component would be the vertical component of force. So that's opposite this angle, so that would be T1 sine 60 degrees and T2 sine 60 degrees. But since they're at the same angle, I could say T1 equals T2. So I could say that's just equal to the tension T. So 2T times sine of 60 degrees equals 980 newtons. Sine of 60 is 0.866 times 2 is 1.73. So I get the tension in each rope is around 566 newtons. I don't know if I can draw a triangle on this. Maybe I can. I don't know if it's going to let me do that sort of shape. Nope, never mind. Okay. So this is a key point. If the T1 and T2 weren't at the same angle, you'd have to think about the fact that the horizontal components of tension for T1 and T2 would be equal, set one of them in terms of the other, and then go from there. That's a harder problem. So key thing with this, look at the symmetry of the problem, recognize the vertical components up is equal to the weight of Tarzan down. Sample 3. So assume a student is dragging a bag of leaves based on the free body diagram shown. Now this is a little odd because it's being dragged horizontally. So that's an applied force. You could also put foot pole or something like that. There's a friction force acting against that, 22 newtons. There's a normal force up of 60.5 newtons, and therefore gravity has to be acting down with 60.5 newtons. Again, kind of a weird units on this or numbers. I think I took it from a physics classroom problem, which is when I use their numbers. So the net force here, if you want to find that, there's no vertical net force because the gravitational force down and the normal force up are equal. So horizontally, we'd take 60 minus 22, and there's a net force of 38 newtons to the right. You could also say east if you want. So to find the acceleration of the leaves, we go back to that master of all physics equations, Newton's second law, net force over total mass, or net force of the mass of the system. So that's 38 newtons. But how do I get the mass? It's not 60.5, but I would take mass is equal to gravitational force or weight divided by gravitational acceleration, which is 9.8. Again, if you want to use 10 here, you would get that the mass of this is 6.05 kilograms. So your answer would be a little different. But the main thing is I need to realize that gravitational force and mass are not the same thing. So I end up getting that this is 6.17 kilograms. Net force over total mass, that gives me around 6.2 meters per second squared to the right. If I want to find the coefficient of friction, this is something we'll learn out of lab, but coefficient of friction is the force of friction divided by the normal force. So in this case, I've got 22 newtons and the normal force is 60.5, so that's 0.36. Again, we'll talk about this in the lab that we do. It's a measure of the stickiness or slipperiness of an interaction. Sample 4 is going to be continued on the next page. So Spencer and Maria are part of the stage crew for theater. They must quickly move a 158 kilogram, which is a lot, baby grand piano off stage by applying a force of 550 newtons to the piano. If the piano accelerates at 1.1 meters per second, or 1.1 meters per second squared, find A, the force of friction on the piano, B, the coefficient of friction on the piano. So I'm going to use gravity's acceleration is 9.8 newtons per kilogram. So first I'm going to draw a free body diagram. It's very similar to this free body diagram in number 3. So the applied force is acting one way, the friction force is acting the other way. The force of the floor, which is the normal force, the force of the earth should be the same. So the vertical forces are balanced. The only forces affecting acceleration are the horizontal ones. So to find the force of friction on the piano, I recognize that, again, this is Newton's second law, net force over mass of the system or total mass. And these two forces are the applied force minus the frictional force, and that would equal the net force. So if we know acceleration, I can rearrange this to say applied force minus force of friction is equal to the mass times the acceleration. So I know that this was 550 newtons, that was stated in the problem. Trying to find the force of friction, 158 times 1.1. So I get a very large force of friction of 376.2 newtons. That's ridiculously large. You would hope something on a stage would not have that much friction. But those are the numbers. The coefficient of friction, in this case moving friction, or objects when they move have kinetic friction, because kinetics means when things are moving. So that's equal to a ratio of the force of friction over a normal force. There are no units for the coefficient of friction because it's newtons on top and newtons on the bottom, and those units divide out. I wouldn't say cancel out, but they divide out. So the normal force on the level surface is equal to the weight of the object. So even though it's not stated, if I know this is 158 kilograms, I multiply that by 9.8, and I get that my gravitational force is 1550 newtons, so my normal force would be 1550 newtons, and I get this, 376 newtons over 1550 newtons, so coefficient of friction, force of friction over normal force, that's 0.24, and again, the units cancel out. That's actually kind of a reasonable number, but on wheels it should be lower than that. Last example, sample 5. I've got a 200 Newton box of donuts hanging from a string. That's C. This is attached to two other strings, A and B. A is exactly horizontal, which is, again, ridiculous, but we're going to go with that for now. It simplifies things. And B is acting at an angle 60 degrees from the horizontal. So it's more vertical than it is horizontal. So to determine the tension in each string, assuming the box is at static equilibrium. So the big idea, the net force at point 8, where these 3 points meet, has got to be 0, as it is for any point in equilibrium. So the first thing I'd recognize is if this is 200 newtons hanging down, the tension in rope C must be 200 newtons. So that's my first answer. That's pretty straightforward. Next, we have to recognize that at this central point, the vertical components of forces and the horizontal components of forces must be equal. So in this particular case, I've got a force up is equal to the force down. We already figured out the force down was 200 newtons. So I'm going to say the tension of this, the vertical component of this tension, is going to equal to 200 newtons. So I'm going to redraw that. I'm thinking this is B, this is C. So I'm going to say tension in B multiplied by the sine of 60 degrees gets me this opposite side component of this tension. And that's going to equal TC, which we found out is 200 newtons. So I get that 0.866 TB is 200 newtons. So the tension in B is 231 newtons. Finally, I'm going to recognize that the horizontal component from string B and all the tension in string A must be equal to each other, because the horizontal forces, or the horizontal components of forces, must also be balanced. So here I'm F equals F down, or force up equals force down. Here I'm force left equals force right, or F left equals fright, since we just had Halloween. Anyhow, that tells me the force on the left is the tension in A, since it's acting directly to the left. The force to the right is the tension in B multiplied by the cosine of 60 degrees. That's this component right here. So I knew that tension in B, I just figured that out as 231 newtons. Cosine is 60 degrees. It's 0.5, so that's about 116 newtons, and therefore that's the tension in A. So that's a more complicated problem. It's a combination of a vector problem and a force problem, and that's why it was the last sample. So hopefully these help you out and worth your time when you're doing your practice homework.